All right. So we are now looking at two masses. So we're gonna show. So we got a little, we got a mass over here and another mass over here. And when light radiates out of a mass, so say this one over here, it radiates outwardly, kind of in all directions. But in between the first mass and the second mass, which is, this guy over here, there is a line, an area of lowest potential. Like the masses are the high potential. So now I got this kind of dotted line here. And what happens is, in Russell's concept, when light radiates out away from a high potential towards this low potential, and it's going to reach this dotted line. Now what ends up happening is that the radiation, which we know spreads outwardly from the inside, from the midpoint, it turns into gravitation, which we all know goes inwardly towards the center of mass. All right, so that's just one concept that I just wanted to show you guys, and this happens in between every mass in the universe. Every mass radiates and gravitates. So there's but it's not just like gravitation spreading out all the way to where it hits here. Like if this was like the sun, this was the sun and this was the earth, the light doesn't just spread all the way out like that. At some point in between the sun and the earth, there's an area of lowest potential, the inertial line, or a plane of zero curvature, because there is actual curvature around, and as it spreads out, the curvature becomes less and less, less and less curved. Like it's very curved over here when it's close to the high potential, but as it gets to lower potential, the curvature becomes less and less until you reach this midline of zero curvature. And after that point, the radiation that's coming out in a expansive radiative way turns into a contractive gravitative way. And so it all starts contracting towards the center, and it hits this high potential area, say like it was the earth, and so the light is essentially regenerated, because that's what gravitation does. It brings light together into a higher potential, to where, even if it's high enough, we can see the light. We can't see the light when it's out here in space. Like if this was the sun, when it's out here in space, it's just blackness. It's so low potential we can't even see it. But once it crosses that plane of zero curvature and it starts to gravitate, and instead of spreading out, it starts contracting inwardly, it gets to higher and higher potential, to the point where we can see it, and we feel the sunlight on our on our hands or face or whatever. So anyway, this is just an important thing to show you about how radiation turns into gravitation, and it radiates away from this high potential and lowering the potential of this one, and then it gravitates towards this one, after it passes the midplane, and raises the potential of this one. All right, so now today we're going to talk about our foundations of physics, and we're going to be looking at J.J. Thomson's experiment where he discovered the electron. And so what I've drawn here is essentially, this area here is a cathode tube. It's essentially a glass tube, and most of the air has been pumped out of it to make it a very low potential area. So first we're going to talk about the traditional experiment that J.J. Thompson did, traditional science, and then we're going to compare it to how Walter Russell's concept would explain the same thing. Okay, so generally, and you guys can look this up online, I'm just going to go through it kind of quickly. You know, the cathode tube had like a metal piece here and a metal piece over here, and there was a high voltage source. I'm putting it down here as a battery, but it was some kind of high voltage source. The point is there's like a positive terminal and a negative terminal, and the idea is that electrons would flow to here and be attracted to the positive, or the anode, the cathode over here is what we call negative cathode, and the anode is the positive. So you can imagine the electrons flowing through the wire, then they would go across here, straight across, be attracted to the anode, which would then, travel along the wire back to the positive, because the negative, they would say, is attracted to the positive. And so what would happen is they would see a beam of electrons going straight across. And let's see, let's use we'll just kind of do this. Okay, that's like our beam of electrons going across. Now, the next thing they did, they added plates. So they took another voltage source and they said, okay, it's going to come out the negative here. It's going to go up. It doesn't touch with that wire, so it goes up. So, and so this plate here would be negative. And then there would be this other one coming around. Oops. Sorry about my drawing here. And it would be connected to the other plate. So this would be the positive plate up here. Positive and negative. And so when they shot the beam this time, they would see that instead of it going straight across, it would curve. And they thought, well, the beam is being attracted to the to the positive plate. And they actually flipped it around the other way. They switched the leads here, so that the wire from the plus terminal would go to this plate, and the wire from the negative terminal would go to this plate, changing the polarity of these plates. And when they did that, they would see the electron beam then curve this way. Okay? So it made sense to say that, if this stream curves when we put an electric field here, it must be made of charged particles of some kind. And they additionally used a magnet instead of, like this is an electric current here, but they just took a regular magnet and they could put a magnet on the, let's see, let's draw a bar magnet here. And, a bar magnet, you got a north and a south. And when they put the magnet near the stream, it would also bend depending on which way they had. If they had it one way, it would bend up. If they switched it around, then it would bend down. And so it made sense that, like, wow, this must be a charged particle, because it's responding to a magnetic field of a magnet, and it's responding to an electric field of a battery circuit with plates, charged plates. So that's pretty straightforward. You guys can find much better explanations and videos on YouTube, but that's the general thing. But what I'm here today to do is now to compare the way that Walter Russell's concept would look at the same exact experiment. So as some of you may already know, in Walter Russell's concept, there's only two forces, gravitation and radiation. And so we're going to show how this experiment is explained by those two forces. Now, in terms of attraction and repulsion, Russell explains that everything is just potential out of place. It's potential trying to find its equilibrium place. What does that mean? You can look at some of my other videos where I do go more in depth about, what potential is, and definitely my the video on the 2023 homecoming at the University of Science and Philosophy explains all of that. So go check that out. But in general, a battery down here will be polarized. There is a potential difference between one side and the other. Okay? And what that means is that in Russell's concept, there's more on this side and less on this side. Now we'll have to thank Benjamin Franklin for the switching around the positive and negative, but that's you guys can look up conventional current and Benjamin Franklin and learn about that. But in this case, because J.J. Thompson was talking about electrons coming out of this negative terminal, that's what we're going to go with. So in Russell's concept, this side of the battery would be getting charged up, meaning stuff would be going because of a chemical reaction. Like say this was a battery, it'd be a chemical reaction. Or if it wasn't a battery, if it was some high voltage source, there'd be some voltage that was created across these two such that there'd be more pressure on this side and less on this side. And so what happens is when there's more pressure on this side and less on this side, the equilibrium has been broken. It's not balanced anymore. And so the potential that has gathered over here, the more stuff over here, wants to go back. It wants to go back to here so that it can get back to equilibrium. That's what potential does. It wants everything, all matter in the universe, Walter says, essentially is just potential that's out of place. And so it's moving to find its perfectly balanced place, which would be a surrounding that had the same potential as its own self. So what happens here? In Russell's concept, since this has been gravitated, this area here, like stuff has been put over here, it now wants to radiate outward because it wants to get back to this side. But we're giving it a path. This time we're going to give it a path of this wire and through here. So the radiation is going to come out of here, out of this terminal. It's going to essentially charge up this wire in the same way that I showed you before. Anytime something is radiating, it will then start gravitating or charging up the next thing that it goes to. So this terminal radiates and charges up this wire. Now the wire is charged up. It wants to radiate, so it will radiate out this way and then charge up this wire. This wire then wants to radiate and charge up here. And the reason why it wants to go here is because this is where less is. There's more over here and there's less over here. So it's drawn to here, back to where it started, to find balance. It wants to essentially go until the battery is just equalized, which then it would be, the battery would be dead, right? We would call it dead, but it would just be back in equilibrium before it was polarized. Now, let's talk about, so that's why now Russell wouldn't call these electrons, he would just say it was light. That's why the light radiates in this direction and comes back to to equalize the polarization, to bring it back to equilibrium. So now, what happens when we, so that's the explanation of the straight across. Now let's talk about this green curve and orange curve. Now when we add this second battery, this is also, same thing as this, it's polarized, all right? There's more stuff over here, and so that wire then essentially charges up this plate. There's more stuff here. So because there's more stuff here, it wants to radiate. It wants to radiate. Now, it will radiate outwardly in all directions, but going towards this plate over here, once it reaches a certain point, it will gravitate, as I showed you before, and it will charge up this plate, and it will end up going back to the battery, to same thing, to oh, sorry, my light turned off there. Let's turn that back on. So it will go back to this battery to get to equilibrium. Okay, so now, so what happens when we turn on this battery, and this is happening? We have this radiation, you know, going essentially up. Oh, sorry guys, my battery is low on this light, so we're just gonna, sorry, you just have to deal with the shadow right there. But okay, so we have this radiation coming from this side that had more towards this side that had less. Once that process starts happening, once this battery is on, and then we turn this battery on, well, what's going to happen is the light's going to come out here, go on the wire, be attracted, it's going to be attracted to this over here, which is the plus. But it's also going to be attracted to this here because this is a plus as well. And when I say plus, sorry, I should clarify, it's where less potential is. This has less potential because of here. And this has more potential because it's here. Sorry, it's this battery. So the more potential here is attracted to the less potential here. But remember, this one is also more potential and less potential. So there's more potential here and less potential here. So when this comes out and shoots across, it is being attracted to the lower potential of this and this. So that is why it is going to curve that way, because it's being attracted to this, because it wants to actually go up in there through this wire and come back and fill this lower potential. This more potential wants to fill this lower potential. So, and once again, if we reverse these such that the negative plate would be up here and the positive plate would be down here, then when the light came out, it would be attracted to this, which would be the positive plate then, which is the less potential. Same thing as it would be attracted to this positive, which would be the less potential. So that is the reason why the light would curve in the way that it does. Now, the interesting thing there is that we've just explained why this light curves, but it has nothing to do with charge. It only has to do with potential. It only has to do with the thing that all matter wants to do, which is find its proper potential position. If it's a higher potential and it's in a low potential area, it's going to fall towards a higher potential area. If it's a low potential thing, but it's in a high potential area, it's going to fall towards a low potential area. So let's see. Now, the last part would be the magnet. And I think this video would be too long for me to explain the magnet, but I'll say in general that a magnet is created, it's just a piece of iron. Then there is a coil of current that's wrapped around, you know, that that piece of iron. And, you know, usually this is also goes to some kind of electrical, we're going to use the battery symbol here again, that, you know, this would be, you know, plus and minus, you know, this is, you know, the battery is creating this current that goes around the iron. Now, when the current goes around the iron, remember, light comes, and this is in Walter's concept, light comes out of here, charges up this wire, it goes around like that, but anything that's charged up also wants to, if you charge it more, it wants to radiate more, so it radiates into the iron and does the thing just like radiating here. And once it goes to the other side, it will, the other side of the, you know, the plane that I talked about, which is in between all matter, you know, this plane right here, it will then gravitate and raise the potential of the thing that it's hitting, and which in this case is the iron. So that iron gets charged up, okay? And iron just has the property that once you, and they use such a high current to make the iron be magnetized, that even after they turn off the current of the whatever made the current, the iron has a memory of that charging up, that the way that it was charged up. And it's done in such a way, because it's coiled around like that, there's a magnetic field going around the coil and going around each of these, and it makes it so that it's a one-way, let's see if I can kind of draw it. It would come around like this, okay? But it's going in this direction. And because it's going in this direction, this magnet is polarized, where all the memory that it has is everything lines up. All right, so once we take the wire away and everything, essentially you'll have one side of the magnet where there is more stuff, and I think that the more stuff would be on the north side, actually. So it actually should be going that way, but but there's more stuff on the one side and less stuff on the other side. It's charged up in a certain way, and actually, yeah, I can't go into, I can make another video about that, because I don't want to say the wrong thing, but this is just generally, so what happens is that when you put this magnet near this light, the same thing is going to happen. Either it's going to be pushed away, or it's going to be attracted to, because it wants to fill the less space. If you turn around the other way, it's going to be pushed away by because the magnet, which was charged up by this coil, now itself, what happens when something gets charged up a lot? It wants to radiate. And that is the magnet, what traditional science knows as the magnetic field, is, in Walter's concept, it is actually, it's not a magnetic field, it is just the radiation coming from the iron as the reaction to it being charged up by that current that they set up with this. So the current charges it up, that's the action, and now the regular piece of iron, which was not magnetic at all, becomes magnetic and now has a reaction where it is radiating light outward. But we think of that as the magnetic field, and Walter's concept, it is just the same substance radiating out. It's the same substance that got gravitated in and charged it up is now getting radiated out, because everything is simple in that way. So we can describe everything with just gravitation and radiation, just two forces. So I hope that is, I hope you guys see kind of what's going on in terms of Russell's concept. The interesting thing here is that with Russell's concept, we would not come to the conclusion that this was a charged particle that was coming out of the battery and going, being attracted to, like a negative being attracted to a positive. We would not come to that conclusion. We would just come to the conclusion that there was a gravitative, there was an imbalance here. So there's more over here and less over here. And when something is, and this could have been set up by like either whether it's a dynamo or something, or if it's just like a lithium ion battery, it's just a chemical reaction. You can see that too, where more stuff would go on the negative pole and less on the positive. So the electrons is what we would call them, would build up over here, but Walter would just call it light, would be building up over here. And since it got put there gravitatively, pushing it over there, now it wants to radiate it out. It would radiate it out, and of course it's going to want to go to the pathway that brings it back to balance out, back to equilibrium. That action, then the action of the gravitative charging up would then set up the reaction that would then bring it back to equilibrium. And it's the same thing with this battery over here, why this is radiating this way. And it's the same thing that the light would just follow the logical paths, either straight across, if there was no battery. If there's a battery turned on, it's going to go, either up or down, depending on the polarity. So that's all we would come to the conclusion of, is that, oh, well, yeah, we knew that was going to happen. And it has nothing to do with charge. We do not need an electromagnetic force to explain that. It's all explained with gravitation and radiation. And same with the magnet. Now, I know, I apologize. I didn't have time to, because the magnet is a little more complicated, and I would have to do another video on that. But it's essentially that basic explanation that I told you is that, the reason why it would be, go up or down because of the magnet. It's the same reason that it would go up or down because of the electrical imbalance that was set up here. The iron also has an imbalance. So, okay, that's it. I would love to hear you guys, to hear what you guys think about this. This is my first Foundations of Physics. And so we were comparing the J.J. Thompson experiment of how the electron was found, which is a huge thing. And, it is definitely a foundation of physics, because it was the first proof of what they thought was a subatomic particle. Okay, so we're talking atomic structure. So this was a huge experiment. And so I just showed you how Walter's concept would, with the same experiment, the kind of reason why the light would move the way it would move, and kind of the conclusions that we would come to, which we wouldn't really come to some new conclusion that there's a particle. It would just be like, oh yeah, the light is acting the way it always acts in any situation. It's going to, if it's in imbalance, it's going to want to go back to balance. So it's going to move in that direction to find balance again. So, and that happens on all scales. So whether it's, the subatomic scale, or if it's in a galactic scale, with Walter's concept, it is all simplified. It's just gravitation and radiation, and it's just light potential moving to find where it can be back in balance. So that's why it can be a nice theory of everything, because it just kind of wraps everything up on all scales. So, all right, that's it, guys. I hope you please like and subscribe. It really helps the channel out. I look forward to hearing what you guys say in the comments about this. I'll be happy to answer any questions and talk about it. All right, yeah, that's it. Until next time, we'll see you. We'll see you next time. Okay, I still need that tagline. Let's see. How about, let's make sure your experiments match nature, or your theories match nature. That's what we're doing here. We are trying to see if our theories or concepts match observations of nature. And as you can see, Russell's concept definitely matches the observations of nature. Okay, thanks.